Hello, I'm Lou Bloomfield, and welcome to How Things Work at the University of Virginia. Today's topic, skating. Whether you're gliding across the ice, strapping old roller skates to your shoes, or cruising down the sidewalk on a skateboard, you're freeing yourself from the constraints of friction and allowing yourself to move with ease and simplicity. Like ordinary shoes, skates support you vertically. That is, the ground supports the skates and the skates support you. But unlike ordinary shoes, the skates move freely forward and backward, and you can coast. Coasting is what makes skating so fun. Coasting is also an example of one of the most fundamental principles in all of physics, the principle of inertia. That an object at rest tends to remain at rest, and that an object in motion tends to remain in motion. As you skate or watch other people skate, you'll notice a couple of common themes. If you're stationary on a level surface and nothing pushes you, you'll remain stationary. But if something does push you, you'll begin to move in the direction of that push. On the other hand, if you're moving on a level surface and nothing pushes on you, you'll continue moving forward in a straight line. But if something does push on you, you'll speed up or slow down or turn. My goal in examining skating is to explain those observations. That effort will introduce us to some of the words that physicists and scientists use to characterize what they see and measure. It'll also bring up some of the basic laws of motion, laws that date back to the times of Galileo and Newton. When we're done with skating, you'll be acquainted with some of the basic tools that we're going to need as we continue to look at how things work. Here's a question to think about. I'm not going to ask it yet officially, but you should have it in mind as we continue our way through skating. A rotary lawnmower is a machine that cuts the grass by spinning a sharp blade very rapidly over the grasses. The question is whether that rotary lawnmower and its spinning blade could cut the grasses if the grasses weren't attached to the ground. To help guide us through the science of skating, we'll pursue 5 how and why questions. Why does a stationary skater tend to remain stationary? Why does a moving skater tend to continue moving? How can we describe the fluid, effortless motion of a coasting skater? How does a skater start, stop, or turn? Why does a skater need ice or wheels in order to skate? There is one video sequence for each of those questions and a summary video at the end.